where Charles Rezk is going to talk about calculations in multiplicative stable homotopy theory at height 2.
Hi, thank you. Well, that title, I guess, describes this talk. I really want to give kind of a broad overview, and then I'll sort of give an example of a calculation that is easy to do and interesting. There won't be much reimagining in this talk. I apologize for that. Someone wrote this announcement on the board. I don't know. All right, so let me remind you, formal group. I mean, I don't have to say what a formal group is at this point, right? So I'll talk about a formal group over A. I'll just remind you, just in case, that formal group is a kind of coordinate-free version of a formal group law. So it's got a function sheaf, function ring, which is isomorphic in some way to a power series ring. You know, it's a coalgebra. And so this is how you get the formal group law from a formal group, by picking a coordinate on it. Okay. So the key thing I need to tell you is what an isogeny of formal groups is. A formal group, well, it's some kind of Hopf algebra. So there's a notion of commutative Hopf algebra, so there's some notion of a homomorphism. An isogeny is a particular kind of homomorphism. Like that, F, such that if you take the resulting map on function rings, which goes in the other direction, F upper star, there should be finite and locally free. The nice thing about that is when that happens, you have a very nice notion of a kernel. You can do this even more generally, but they're nice if you have an isogeny. So the kernel of F is built by taking the obvious ring of functions, OK, where I tensor down along this map from OG prime to OG down to the ground ring. But the observation is that if you have an isogeny, then this gadget is finite and locally free over A. So it's a finite group scheme over A. Commutative group scheme for A. There's a notion of degree, which is basically the rank of this map, or if you like, the rank of this OK as a module over A. So there's the degree of F. That's just the rank. OK over A. It's really only defined locally somehow, but very soon A will be a local ring, so that won't matter. So here's a non-example. So let's take the simplest example of a homomorphism we can think of. I'll take the multiplicative group. That's defined, formal multiplicative groups defined over Z. And let's take the P series. This is all over Z. So in a coordinate, you know what this is. You pull back your coordinate. It's something like px plus blah, blah, blah plus x to the p. Well, that's not an isogeny. However, if you go somewhere nearby, it becomes an isogeny. So if I go to the rational setting, this actually becomes an isomorphism rationally. Meaning if I look over the base ring Q, any isomorphism in an isogeny. So this is an isogeny of degree 1 in that case. And on the other hand, I could go to mod P, or I could even look over the p-adics. In that case, it's an isogeny. It's an isogeny of degree P. All right. So one thing you learn here is if you want this nice notion of kernel, you have to go to a place where your homomorphisms are isogeny. Since you particularly like the P series, you want to live in a place where the P series is itself an isogeny. That limits the sort of phenomena that you might want to look at here. I'm going to erase this now. Let's see. Here's an example I'll need to talk about. This is the Frobenius isogeny. So if I have a ring of characteristic P, and my group lives over it, formal group, there's always a Frobenius isogeny of P to the rth power. So I'll call it F to the R. It goes from G to a base change of G along phi to the R. Phi is the endomorphism of A given by the pth power map. So I can pull back my group along that homomorphism. And the Frobenius isogeny is also given by that formula. It's given by the relative Frobenius on formal schemes. So that's a canonically defined isogeny that you have whenever you're in characteristic P. I'm writing very large on these boards today. Over a field K of characteristic P, things are even better. Whenever you have an isogeny, let's say this is degree P to the R, all isogenies have prime power, P power degree for the reason that you'll see. They always factor canonically through Frobenius. So I have the Frobenius isogeny, F to the R, and there exists a unique factorization through an isomorphism. So over a field, basically the only isogenies, all isogenies are built from Frobenius and isomorphisms. All right. So what I want to do is I want to fit this into a kind of structure, and I need to therefore tell you about deformations. So I'm headed towards thinking about Morava E theory. So that's a commutative S algebra. I'm interested in power operations for that ring. Morava E theory is associated to deformations of formal groups. So let me tell you how this works. I'm going to fix a single formal group, distinguished, called G0. This will live over K. So K is supposed to be a perfect field, characteristic P. G0 is going to have the property that its P series is an isogeny of degree P to the N. So it's a height n formal group. So I'm going to define the notion of a deformation structure relative to this fixed guy. So let's give an arbitrary formal group over A. A is going to be a complete local ring. And I'll define a set. Let's call this script D of GA. What's this supposed to be? This will be the set of pairs. I'll have an I and an alpha. I is an inclusion of the field K, that K, into A mod its maximal ideal. And then alpha is an isomorphism of formal groups from the base change of G0 to A mod M to the base change of G to A mod M. Let's write it like that. Okay. So if I have a deformation structure on my GA, I say it's a deformation of G0. But I'm going to think of the deformation structure as something a little bit separate. It's a piece of structure you add to the formal group. Here's a remark. I can push forward deformations along isogenies. So if I have an isogeny of such, let's say, G to G prime, this is defined over A, then I have a corresponding map, it's called F lower star, from the set of deformation structures on G to the set of deformation structures on G prime. Well, why is that? Oh, the reason's still up there. It's because of that unique factorization property. Let me write that out. Let's see. Oops, why did I do that? So, well, there's nothing really to say. Right? I have an isogeny, but But then it's a deformation. G is a deformation, or equipped with a deformation structure. So there's an isomorphism alpha from G0 to G at the special fiber, which is A mod M. Well, F, the isogeny, has sort of a base change of the special fiber. Call that F G mod M. And well, the observation is there exists a unique factorization through Frobenius. So phi to the r star I star G0, this is F to the r, and then there's a unique alpha prime. So the formula is F star of I alpha. It's something like, I composed with phi to the r alpha prime. All right. So you can push forward isogenies. Sorry, you can push forward deformations. Here's an exercise that you can do to make sure that you understood the definitions, I guess. So again, if I have Fp is an A, well, there are two different ways I can move a deformation from G to the base change of dG along the Beath power map. One thing I can do is I can push forward along Frobenius. Did I give this a name? Yep, F lower star. F now, capital F is Frobenius. The other thing I can do is I can base change. I can always pull back a deformation structure along a ring homomorphism. So I'll pull back along phi. So this is the phi from A to A that I wrote down before, Beath power map. And the exercise is that these are actually the same. It's supposed to be a tautology. So it's supposed to be an easy exercise. But I won't do it. All right. So I've set up some stuff related to deformations. What's going to happen? Now I'm going to take all these deformations and put them in a pile. This is the pile of deformation structures. So if I have a complete local ring, I can associate to it a category, def A. So there's a fixed G0 here, so I might decorate this with G0, but I'll probably forget at some point. So it's just def of A. It's a category. The objects are pairs consisting of a G over A and a deformation. I wrote IA, I alpha and D of G mod A. And then morphisms, well, they're going to be isogenies. But they're isogenies that carry along this push forward that I just defined one of the deformation structures to the corresponding one for G prime. So this is under F lower star. So you can think of an object here as a formal group attached with this little extra piece of structure. It's a deformation structure, and the morphisms are isogenies that are compatible with the choices of level of a deformation structure. This is actually a functor in complete local ring. So if I have a local homomorphism, then I get a functor from def A to def A prime, which I'm going to call G upper star, even though I guess it's covariant the way I've written it, but that's life. I'm thinking of this scheme theoretically. So you pull back along the scheme map, or in this case, formal scheme map, and you get a functor. So what is this? It's some kind of functor from really the opposite category of complete local rings to categories. Right? It's a pre-sheaf. Maybe it's really a pseudo-functor. Right? There's coherence, I guess, if you probably think this through. It's called a pseudo-functor. Yep. Let's see here. Oh, should this not be op then? Right. Thank you. Yeah, I'll just write it like this. It schemes, it would be op. That's right. So this is a kind of pre-sheaf on these formal schemes, if you like. Well, if you have a pre-sheaf of groupoids, that's a stack, or a pre-stack at least. This isn't a pre-sheaf of groupoids, it's a pre-sheaf of categories, so it's not a stack, it's a pile. This terminology can be blamed on Matt Ando, so I'll blame it on him. But it has to be called something. It's a little bit awkward to call it a stack. Sometimes people have called these stacks in the literature as well, but somehow that's not really, they're a little bit more. All right, well, now I want to talk about quasi-coherent sheaves. There's no descent here, really. There's actually, there's going to be, although I'm going to use the word sheaf, there's no particular descent condition I'm going to describe here. In analogous situations, you would want to have a descent condition. This particular one doesn't really make any, there's no need to talk about that. On def, so let's spell this out. This will be called quasi-coherent def. So an object, M, it's really a collection of functors, M sub A, and a collection of natural transformations, M sub G. So the idea is that if you have an A, that's a complete local ring, there should be a functor. That's going to be a functor from def A, and this here, do I want an op? Def A op to mod A, to the category of A modules. And then for G also, G is a local homomorphism. This will be a natural transformation. So I'll have a natural transformation from, on the one hand, MA takes values in A modules, but then I can tensor it up, that A module, along the ring homomorphism. On the other hand, I can take MA prime, and I can compose that with the operation that on the other board I called G upper star. That was this functor here. And this I want to be a natural isomorphism. That sort of is the quasi-coherent direction. And then this should satisfy some coherence that is more or less obvious. Again, I wanted to say it was some kind of pseudo-functor, but I think the other thing was a pseudo-functor, so I'm not sure what this is supposed to be called. A pseudo-functor or something. There's one more level in it, I guess. All right. Here's a couple of examples. There are natural examples of quasi-coherent sheaves on the deformation category that are actually familiar. Well, this one's familiar. It's called omega. So if I have a formal group, it has a module of invariant one forms. That's always a rank 1 module over A. It doesn't really have a canonical basis, but it's a rank 1 module. So I can associate to each object of def this A module. Of def A, I can associate this A module. And then I have to associate something to an isogeny. So I have to, therefore, if I have an isogeny from G to G prime, I have to be able to take an invariant one form on G prime and pull it back to G. That's the op and the def. But I can pull back one forms along homomorphisms, and certainly, therefore, along isogenies. So this is an example of one of these guys. So this encodes the fact that I can pull back forms along isogenies. Here's a slightly more stupid example. I'll call this degree. This will also be a rank 1 module. In fact, degree sub A applied to any formal group is just set to be the module A. But I have to tell you how to pull back along an isogeny. I associated a positive integer to an isogeny, namely its degree. That's what I'm going to pull back by. So F star, pulling back along an isogeny, is multiplication by the degree of F, which is an integer. Okay. That is also an example of such a thing. Okay. Are there questions? So I've just written down a definition. I want to digress for a minute and talk about not formal groups, but elliptic curves. So this notion I've just defined is fairly flexible. There's nothing particular about formal groups I used other than that it was sort of a category where the morphisms were isogenies. So I could transplant this idea to various other situations. So a digression here. So instead of talking about formal groups with deformations, deformation structures, I could talk about elliptic curves. So I could replace the role of complete local rings with schemes. And I could replace the role of formal groups with deformation with elliptic curves. And I could replace the role of isogenies that preserve the structure to just isogenies. And this gives me a pile, which I'll just call L. But maybe I should decorate and say it has something to do with isogenies. So it's the pile of elliptic curves and isogenies. It's a perfectly good notion. You could also play games. You could also just look at pth power isogenies. You don't want all isogenies. Let's just take some of them. That would be something like the pile, pill, elliptic, p isogeny. Okay. And then there's a definition of quasi-coherent sheaf on the pile of elliptic curves and isogenies. Here I do have to be more careful. Here I do have to take into account some kind of topology. Sometimes I have the stack of elliptic curves, and I should look at sheaves over those, and then I should have various maps between those sheaves under pullbacks along some maps of morphisms of sheaves associated to the stacks that classify isogenies. So let's just say that there must be some notion of quasi-coherent sheaf on L isog. The reason I want to mention this is that you consider actually write down examples here too, even though I've barely told you the definition. Maybe for later reference. Here's an example that comes up in elliptic curves. So let's see. If I have a curve, elliptic curve, I can think about its associated de Rham cohomology. This is in the algebraic sense. So there's an algebraic de Rham cohomology defined as the hypercohomology of the algebraic de Rham complex. So I'm going to think of the value here. I didn't maybe choose the right notation. This is really some kind of form relative to S. So this would be some kind of push-forward hypercohomology down to the scheme S. So the result here is supposed to be a coherent sheaf over S. And then you can let this vary as the curve varies. This is a functor. It certainly defines a coherent, if you put this together for all S, for all elliptic curves, this gives you a coherent sheaf on the moduli stack of elliptic curves. But de Rham cohomology is also a functor. So in particular, I can apply this to isogenies. So this gives me an object, let's call it HKdR, that's in the quasi-coherent sheaves on elliptic curves with isogenies. Let's say a little bit about this. So how do you compute this thing? Well, there's a hypercohomology spectral sequence, which is also called the algebraic Hodge to de Rham spectral sequence. So that degenerates for an elliptic curve. So you learn things like this. Well, H0, that's just the structure sheaf of the base. H0 is trivial. H1 fits in an exact sequence. On one side, there's, let me get this right, H0 of the cotangent space, the Kähler forms on the curve. And on the other side, I have, I guess, H1 of the structure sheaf of the curve. So this is usually called something like omega. These are global sections over the curve, relative to the curve, of one forms. They're also invariant one forms, the group law of the elliptic curve. Serre duality identifies this as something like omega to the inverse. Well, this is an exact sequence of sheaves over the moduli stack of elliptic curves, but it's actually an exact sequence of objects in the quasi-coherent category of quasi-coherent sheaves in the pile of elliptic curves and isogenies. This sequence is compatible with pulling back along isogenies. as an object in sheaves on the pile, I'll call this omega. It's not right to call this omega inverse because there's something you have to encode about the way that isogenies act, isogenies that aren't just isomorphisms. So I usually write here omega inverse tensor degree. That turns out to be the right answer. There's an adjustment that to explain how that interacts with isogenies, you have to think about how degree works. There's also H2. And this actually, as a sheaf in the pile, is just that degree sheaf. You can see the Serre duality that's relating these two things as a pairing to this. This is degree because there's a fundamental class in the elliptic curve. You pull back the fundamental class, that gives you the degree. All right, so if this exists in this world, in particular, I want to note this gives you an element in X. I'm going to write X here, but maybe I mean morphisms in the derived category of quasi-coherent sheaves. So interpret this as you will. So we get this Hodge class. Let's just call it the Hodge class in X. This is over L with isogenies, omega inverse tensor degree, omega. You can compute things about these kinds of groups. So here's a remark, which I won't really flesh out right now. Let's think not about elliptic curves over arbitrary lengths. Let's just think about elliptic curves over the complex numbers. And let's just restrict to p isogenies. I can still think about extensions in that world, the same objects. You can produce a whole bunch of these. I'll actually tell you where they come from. They come from modular forms suitably chosen. So I can look at modular forms for the congruence group gamma 0p. This is over the complex numbers now, of weight 2. And I have to take a subspace of this. I'll write here capital W equals -1. Capital W is the Atkin-Lehner involution on modular forms. And this is the eigenspace -1 for that involution. This appeared in Kirsten's talk on Monday at Berkeley. Involution. So there's a map. It's actually an injection. And the Hodge class, you can name the Hodge class. This class comes from a particular modular form of weight p called the, or level p, called the level p Eisenstein series. So E sub 2p. So I don't want to get in too much into detail about modular forms. There's this modular form for gamma 0p called E2p. Its Q expansion is E2q minus p E2q to the p, where E2 is the Eisenstein series of weight 2. This is -1/12 plus some stuff. Okay. Sort of famously, this series is not actually a modular form. It looks like the other Eisenstein series, which are modular forms, but this one isn't modular. If it were a modular form, it would give a splitting of the Hodge extension in this quasi-category of sheaves on the pile. So the failure of E2 to be a modular form is exactly the obstruction to splitting that as in this category of sheaves on the pile, which means with respect to isogenies, or p isogenies in this case. You can actually split the sequence algebraically if you invert 6, if you just care about isomorphisms of elliptic curves over the stack of elliptic curves. But if you care about isogenies as well, there's a much more prominent obstruction, which involves this. So that's just, I wanted to mention that just because it's kind of neat that you could actually do such a calculation. I haven't told you how you would even say this. It's not actually very hard. And also because it may come up later, if I have time. One thing I want to say is I think this is kind of an interesting object, this quasi-coherent sheaves on the pile of elliptic curves. And I would like it to have something to do with algebraic topology. Because, so I'm going to tell you in a little bit that quasi-coherent sheaves on deformations have something to do with Morava E theory, which is a particular commutative S algebra. I think the story should be that this gadget has a similar relationship to some kind of notion of globally equivariant ultracommutative ring spectrum associated to topological modular forms. And I think that's the right conjecture, and you can see bits of this. I'm not really going to say more about that. So this should have. Yep. It's roughly, yeah. I'm going to actually write down a version of that, I think, and you can tell me if that's what it is. I'll do it for deformations. I mean, it's something very precise and not really all that difficult. Should have something to do. It's sort of a elliptic cohomology as, I don't know, an ultracommutative global ring. And if you spell this out, you're going to have to worry about EDAG. And I guess you're also going to need plethories in Clark's sense. I mean, I'm pretty sure that both those ingredients we saw this morning are going to play a role in describing this. All right. So I'm going to return to deformations now. All right. So I introduced this category of deformations, or I introduced this pile of deformations, def. Let me make an observation. So what I did is I talked about formal groups and then I attached a deformation structure. So let's fix G0 over K. So there was this set DGA of deformation structures, and one reason for introducing it is that the automorphism group of the formal group acts on it, and it acts faithfully. Sorry, acts freely, that's what I should say. This has a consequence. This means that in the category def G mod A, or sorry, that's called def A, there's no G there. In the category def A, there's, between any two objects, there's at most one isomorphism. So in terms of Chris's talk yesterday, it's a zero truncated object in cat. This is let's use this notation, I like that. And the groupoid of objects is sort of is discrete homotopically. So I may play the game, therefore. You can't usually do this. I can now just identify objects that are isomorphic formally. So I'll build the quotient category where I identify isomorphic objects. That's actually equivalent to def. And I can do it because of this funny feature. Def actually has a kind of grading because I've talked about the degree of an isogeny. So let's write def R for the set of morphisms of degree D, of degree P to the R. Def R, this is morphisms of degree P to the R. Let's mod out by twiddle. That's in one-to-one correspondence, it turns out. Oops. I got ahead of myself here. That's a one-to-one correspondence with pairs, G and K, where K is a subgroup of degree P to the R. So G, if you like, is an element in def 0 mod twiddle, and K is a subgroup. The idea is, if you have a morphism, it has a kernel, and that completely classifies this data. So this is the kernel now. Okay. Here's some theorems, which I won't say much about. This is Morava, Gorse, Hopkins, Miller, and Strickland. It's an omnibus theorem. there exists an essentially unique commutative S algebra. Essentially unique commutative S algebra. E, it really depends on the formal group G0, which is in the background, such that, oh, I forgot to say something. Darn it. I skipped a line. Oh no, this is terrible. Such that, and to say the such that, which will go in here, I have to say another theorem. So this theorem comes before. It's due to Lubin-Tate and Strickland. Again, an omnibus theorem. The theorem of these guys is that def is representable. So there exist complete local rings A sub r that represent this set def RA mod twiddle. Twiddle, that's right, B here. So it doesn't look like A. This is hom in complete local rings from AR to B. Ugh. Right. A0 is the ring that's due to Lubin and Tate. That's this deformation space for height n formal groups. So abstractly, it's this power series ring on n-1 variables. And then, this was theorem 1, and then theorem 2 says there exists a unique commutative S algebra such that right this way, the E0 cohomology of B sigma P to the R modulo a certain ideal is isomorphic to AR made 2 periodic. I is an ideal generated by transfers. So I is the ideal generated by transfers from proper subgroups of the form sigma I cross sigma P to the R minus I inside sigma P to the R. There's other ways to say that, but that will work. Okay. In particular, B sigma 1, that's just E star. I should put here a star, by the way. This was graded. Excuse me. E star is A0, as you probably guessed. Okay. So in this case, the theorem's about the AR for R bigger than 0, and those all are due to Strickland. He actually wrote, not in this form, and this is why I mentioned the previous line, he described AR in terms of subgroups of a formal group. It's the thing that classifies subgroups. And that line upstairs makes that clear. All right. So you put all this together, you discover that this category, this pile, is represented by an object. It's actually a graded category object in formal affine schemes. So you get this graded category object in the opposite category of complete local rings, which is associated to this collection of rings. And the category it represents is this def, or the pile it represents is this def object. Okay. Oh, in particular, of course, I'm supposed to read off now that, guess what quasi-coherent sheaves on def are? Well, they're comodules in some sense. So an object in here, called M underline, those really correspond to, well, they're E0 modules, or A0 modules, together with some kind of coaction, which will look something like this. Psi R parentheses, and then satisfies the axioms for a coaction. So this weird category of sheaves on deformations is actually algebraically accessible in this way. So the observation is that this is what you need to describe the theory of power operations in Morava E theory. Here's the idea. So if I have a commutative S algebra, actually let's have it be a commutative E algebra, because E is a commutative ring. And I'd like it to be Kn local. I'll say why in a minute. Then the power construction gives you a function from, let's say, pi 0 of R to the spectrum of functions from the classifying space of the symmetric group into R. Let's call this P sub M. What you can understand about this construction has a lot to do with what you can understand about this, the cohomology of the symmetric group. In this case, and in fact I'm going to use the fact that R is Kn local here, this is really pi 0 of R tensor over E0, the E cohomology of the symmetric group. Let's see, there's a quotient of that cohomology which we called AR. So this is really this. So I get a map here called psi R. The power construction is not usually additive, it's multiplicative. M has probably turned to P to the M here. So M is now P to the R, starting there. And let's see, anything else I left out? I guess that's it. This is a ring homomorphism. And it's exactly a coaction. So this makes pi 0 of R into one of these quasi-coherent sheaf gadgets on def. So that's the sort of the structure that you have, and you have to now unwrap this structure. Actually, you have to add to it. I'm going to maybe be a little bit brief about this. I could spend another hour saying what else is going on, but I don't want to. So, how do I want to say this? Well, out of this category of modules, you can extract a category, which I'll just call A. Position. So there exists a category, script A depending on G0. I wasn't going to say this, but Clark told you what a plethary was this morning. This is an E-star plethary, or it's a category of algebras for an E-star plethary. So they have an action by this plethary. But I have to, of course, tell you what the plethary is. And roughly speaking, well, this here is the category of Kn local commutative E algebras. That's right, commutative. So I already wrote down a functor to E modules, homotopy. Somewhere, of course, there's not just pi 0, there's pi star, there's a grading. And I'm just not going to tell you exactly how you do that. It can be handled. There's this category A, and we can lift this functor to A, which I'll also call pi star, by lack of imagination. I have to tell you, though, something about A. It's very closely related to a category of sheaves of quasi-coherent rings. So I can look at quasi-coherent sheaves on def. So far I talked about sheaves of modules. Well, it's actually a tensor category. So there's a sheaves of rings. They're actually some kind of graded rings. I'll put a star here, but don't pretend you know what that means. It's a little bit of subtlety to say what this is. There's actually a further refinement, which I won't say too much about. I'll put frob here. This is going to be a full subcategory. Let's just write FRB, that's all it fits. This will be a full subcategory. And this forgetful functor, the modules, factors through this. This functor, from A to this funny category of quasi-coherent sheaves of rings graded with a Frobenius congruence, is nearly an equivalence. More precisely, it induces an equivalence on p-torsion-free objects. So let's call this U. Let's say over here, U restricts to an equivalence on p-torsion-free objects. There's an additional set of business about completion, which I won't tell you about. There's a preprint by Bartle and Franklin to actually clear up some issues about that. So there are things you can say that are precise, but I think let me not say anything. The interesting thing about this is that you can actually reconstruct A from this category, which I've almost completely defined for you. I haven't told you what the grading is, and I haven't told you what FERB means, this full subcategory. In fact, A has free objects, free algebras, which happen to be p-torsion free. The full subcategory of free objects is equivalent to a full subcategory of this guy. And once you know the free objects, you can reconstruct the whole category A. So you can actually construct the category A just from knowledge of this. Knowledge of this only depends on the formal group G0. So this is all stuff that only depends on G0. So that's sort of how you can lift pi star to a functor to a fancy category, which captures operations. Okay. I don't want to go into all the details. I just want to tell you that such a thing exists. Maybe I'll say a little bit about the FRB. So, just because it's worth saying. The idea is that, so a sheaf of rings, quasi-coherent sheaves of rings on def, satisfies the Frobenius congruence, Well, here's the thing. So remember, what's an object in here? It's something I can evaluate once I choose a ring, and then I choose a formal group over that ring together with a deformation structure from G0 to that guy. So that's a value of R at something. But remember, it's a functor with respect to isogenies, and so one kind of isogeny is the Frobenius isogeny. Let's do the degree P Frobenius isogeny. So that goes from RA phi upper star G, and then there's some kind of F lower star I alpha. That was the notation I used. And I think I have the map the right direction. This is F. I don't know now if I'm supposed to call this F upper star or F lower star. I'll just call it F. I think I had you do the exercise where I told you that if you push forward, this is, of course, I'm assuming here, Frobenius has to be defined, so we're in characteristic P. I gave you the exercise that pushing forward a deformation along Frobenius is like pulling back along the Pth power map. So this is really A, RA, phi upper star G, phi upper star of the deformation. And remember, the formation of R is compatible with base change. So that's the same as tensoring up RA of the original guy, G I comma alpha, along phi. There's another map here sitting around, which is the usual relative Frobenius of rings. And the Frobenius congruence says that this diagram commutes. It's a congruence because it involves modding by P somewhere. So when you see it algebraically, you see it as involving something about dividing by P. Let's do an explicit example where I'll tell you the answer, because and it's very nice. I don't even actually have to tell you what it is. I just have to tell you it's the thing that Clark mentioned in his talk. So the example, if I take G0 to be the formal multiplicative group over FP, that's height 1. Then, well, there are all these rings AR, which classify subgroups, but there's only ever one subgroup of order P to the R. So those are all actually ZP. The deformation space of the multiplicative group in this sense lives over ZP. And those, of course, form some kind of coalgebra. So a quasi-coherent sheaf of modules is really the same as a module over ZP together with an involution, which I might call psi. It has an operation, which you'd call the Adams operation. What's a quasi-coherent sheaf of rings which satisfies the Frobenius condition? Well, now you have a ring which has a ring endomorphism, And it satisfies a congruence which says that psi of x is congruent to x to the p mod p. The Adams congruence. Okay, what's A? Well, what you do is you end up putting in a function that witnesses the congruence. This is what's called a theta ring. So A is actually the category of p-complete graded theta p rings in the sense that Clark mentioned this morning, except without the grading. The grading's not hard to put in. Okay. So this whole algebraic nonsense is basically just a way of reconstructing definitions that look like that. Right? And for height 1, it's sort of something we already knew. For height 2 and higher, maybe we didn't already know it. And so now you might wonder, well, can you say anything about it? How am I doing on time here? Oh, dear. Let me just say that you can. So I'll make one remark about this. I'll make two remarks. Remark 1. You can show that this coalgebra A sub R, it's a collection of such, it's essentially quadratic. So you have to give an A0 module, and then you have to give some kind of coaction that says what happens when you push forward along isogenies. But somehow all isogenies are somehow morally can be factored into pth power isogenies, just power p, just of degree p. Rather, not pth power, degree p isogenies. So you only actually have to supply the information for degree p isogenies. So the data of this graded category object, and this sort of comes with sort of extra structure, is completely determined by, well, you have to give A1, that classifies the degree p isogenies. There's some source and target maps you have to worry about. One more thing you have to do, though, you have to worry about relations, because if there are several different ways you can compose degree p isogenies to get degree p squared isogenies. So you have to worry about A2, which sits inside A1 tensor over A1 A0, and this has something to do with composition. And that's it. That's the only thing you have to supply. Everything else is generated by this data. Possibly I should say co-generated, because it's a coalgebra. At height 2, things actually simplify a little bit more, because at height 2 there's a good notion of dual isogeny, which turns out to preserve degree. So there's actually an involution of the ring A1 corresponding to taking the dual isogeny of an isogeny, of a degree p isogeny. You can actually recover A2 from that. That thing I usually call W, because it's related to that Atkins-Linear isogeny I said, involution I mentioned for elliptic curves. The Atkins-Linear isogeny, Atkins-Linear involution is exactly the involution associated to associating an isogeny of elliptic curves to its dual isogeny and its effect on modular forms. What else do I want to say? That was the first remark. The second remark, which I'm not going to spell out, I just don't have time to do that, which is too bad. This category has finite homological dimension. It's basically 2n. It is the height. N of that actually just comes from A0, because that's a dimension n. And the other n comes from this structure of keeping track of the isogenies. Furthermore, there's an explicit way to build explicit resolutions, kind of a Kazul complex. But since I have a very small number of minutes, I won't say that. So for height 2, there's a 3-term complex you can use to compute x, as long as the underlying modules are projective over A0. And it involves thinking about the object. You have to sort of plug in A1 and something about A2 in order to write down that complex. It turns out you can actually build the exact analogous complex over elliptic curves. So I alluded to some weird calculation that I claimed I could do for elliptic curves, but it actually uses the exact same formalism. You can do it in that setting exactly the same way. So that wasn't just sort of Wow, it's actually the exact same thing. So these are both theorems, and they require some work. Somewhat annoyingly, at heights 3 and above, the only proof I know goes through topology for both of these facts. I actually have to start thinking about, well, it's a long story. At height 2, you can give a proof that's geometric, and that's why I know it's true for elliptic curves as well. It's probably true, you can probably give geometric proofs in a general setting. All right, let me just close now by describing a calculation, which I promised had something to do with a calculation. And I should say one more thing, is that you can actually explicitly write down what these objects look like at height 2. Certainly at low primes, this has been done, 2 and 3. If you're willing to tensor with z mod p, you can actually describe everything at height 2 explicitly, in terms of explicit formulas. And that's what the calculations I know are based on. So there's a spectral sequence you can use now actually compute the E2 term for. So I'm going to take some augmented K and local commutative S algebras, commutative E algebras. Well, there's some spectral sequence you can cook up that computes the homotopy groups of the mapping space. So these are augmented E algebras over E. That's the augmentation. Now, of course, to use the spectral sequence like this, you need to have an E2 term that you can understand. So let's just say that if R, pi star of R, is concentrated in even degree and smooth in a suitable sense, then you can write down the E2 term as follows. Well, in degree 0, 0, this is just going to be maps in this category A, from pi star of R to pi star of F. Maybe A augmented over pi star E. Just maps in this funny category I haven't described. If we're smooth, then we can describe the other parts of the E2 term as xed in quasi-coherent sheaves on def. This will go from the indecomposables of pi star of R to the augmentation ideal of F. I put space in there because I'm going to put something which I won't explain. Extra omega to the minus 1s. Don't let that bother you. Sorry? This is the 0, 0 term.
Yeah, what is it? I can't read it.
It says A over pi star E, pi star R to pi star F. The A is that A. Over pi star E because they're augmented. It's 0, 0. Oh, and there's an extra t here. So let me put in here. This is t over 2 minus 1 is what goes in the exponent here, not just minus 1. And this is for all other S and t. So you can compute this in terms of this xed. So here's a sample. So there's a conjecture due to Hopkins and Lurie, of which this is a special case. So I'll call this a proposition in this case because I can prove it, although the word on the street is this is actually now a theorem in general. But so I'll take height 2 G0 over FP bar. Here's something you might want to compute. I'm going to compute, let's do this actually, S algebra maps from the suspension spectrum of the integers, that's a ring because the integers are an abelian group, to E. And this is supposed to be a space which has a discrete part and another part which is an Eilert-MacLane space. So this is so I can prove this using these calculations. This is just the space, oops, there's no equals there. This is the space of maps, derived space of maps in the category of commutative S algebras. This is commutative S algebras. Sorry. Does that make sense now? No? Okay. This is less exciting than it looks because of Ravenel's-Wilson's results on the Kn homology of Eilert-MacLane space. You actually know this is a 3 truncated object. And, well, I think pi 3 has been sort of known to lots of people. It's in the paper of Soddy and Westerland, for instance. But so it's the lower homotopy groups that are the ones you have to calculate. So it's maybe not so surprising. This is not an amazing result in this case. It's really an example of this, right? This is really something like commutative algebras. This was also commutative algebras. I hope this was clear. Yep. Commutative algebras. E over E, can local. You know, you take the E smash this. You can localize. You get E cross E. So this is an example of this. So I can plug in my spectral sequence. So the observation, of course, is that the spectral sequence degenerates. This is the only thing I want to tell you. There's a 0-0 piece, which is the source of the FP bar cross. And all the other STs vanish except for 1, 4. So that's X'd in quasi-coherent sheaves of omega inverse. Well, it turns out the indecomposables of suspension spectrum of E homology, the suspension spectrum of Z, as an object in this quasi-coherent sheaves over def is the degree sheaf. And then on the other side, if I have the numbers worked out, that's 4, 2, 2, minus 1. And this is just the trivial sheaf. So this is just actually omega. And this is the only non-trivial group, and it's ZP. So that's the calculation. You just have to compute the E2 term. Really, you compute it mod. Everything can be computed mod 2. That's enough. Mod P, rather. That's enough. OK, so of course, this was, of course, the exact kind of calculation I showed you for the elliptic curves. And I pointed out that in the elliptic curve setting, so quasi-coherent sheaves on elliptic curves with isogenies, same names for these things. There is a particular distinguished class, which was this Hodge extension. Well, that does actually go to the generator here. That's something you actually read out of various papers of Nick Katz. It sort of shows up in various guises if you look at that. So the interesting thing about this calculation is not actually the fact that it can be done. I don't think it's surprising or sort of, it's a nice fact. But the fact that somehow you can give this name to the generator. I would like to really understand what that means. That seems to be more important than merely doing the calculation. You can actually do a little bit better, because you can actually use this to compute, say, maps, commutative algebra maps from suspension spectrum of Z into, say, the P completion of TMF, because by Ravenel-Wilson, this is really just a K2 local problem, and you certainly know TMF K2 locally. So this turns out to be a product of copies of ZP indexed by a number CP, which counts supersingular curves in a certain way. The interesting observation, of course, is this actually also dovetails with the other thing I described. Remember, I wrote down this collection of elements in here, which involved weight 2 modular forms for gamma 0p, where the Akinlaver involution had eigenvalue -1, and that's the dimension of that space too. It's not, by the way, it's well known that this gadget is related to supersingular curves. I think that's basically an observation of Ogg. So the fact that those number appears in both places is well known, but somehow this connection I'd like to understand better, and what it has to do with this more general hypothetical EDAG plethora TMF elliptic curve story. All right, I'll stop there.